So today we're going to talk about the rational method. This is a very simple approach that is very commonly used in civil engineering, and the primary purpose of it is to calculate the peak runoff so that we can size culverts and storm drains. Now, in the previous couple of lectures, when we learned about hydrographs and the NRCS methods, we were really trying to get a plot of the flow rate versus time, a hydrograph. And the purpose of that hydrograph was, there's a couple purposes. One was to understand, to get the peak flow so we can size infrastructure. Another is to get the total volume of runoff so we can size things like detention basins and so forth. But in this case, we're just going to have an equation to calculate the actual peak flow. Okay? Very commonly used, and for people who go on to do sort of general civil, like working on subdivisions and developments and so forth, this is going to be a very commonly applied concept, maybe the most commonly applied concept from this class. Okay? So the NRCS methods that we've talked about already are applicable to large areas. We used HEC-HMS to apply it to a large watershed. You could apply the NRCS methods to like the Hess Creek watershed, for example. But what if we want to look at like a parking lot or a residential lot? What is the peak flow coming off of those so we can size the storm drain draining that parking lot, for example? It might only be a couple of acres. For that purpose, we're going to probably use the rational method. All right? Seldom used for areas greater than 1,000 acres. In fact, I would say it's seldomly used for areas greater than even like 20 to 30 acres. And we'll talk about later when you might use one method versus the other, look at some regulations and so forth on that. But all right, so the formula is very easy to remember. It says Q equals CIA. Okay, let's make that red. And we're going to make it Arial instead. There we go. Alright, Q equals CIA. I thought about wearing like some sunglasses and a little like spy hat or something as like a little joke when I put that formula up there, but couldn't find my spy hat. So you just have to remember it. Alright, so what do these parameters mean? C is a unitless coefficient related to watershed characteristics, very similar to the curve number. We'll look at it more in a second. The intensity in inches per hour, what's the intensity of rainfall, and the area, the watershed area in acres. And so you can just think about this as saying like how much flow is coming off an area. Well, it's the area times the depth of rainfall, or the depth of rainfall per hour, right? So I multiply those two together and I get a volume per time, which is what I want, flow rate. But some of that might infiltrate or not run off, right? So only a fraction of it does, and that's what that C is for. Is what fraction of what's falling runs off. Very simple. Maybe when you were in fluid mechanics and you were looking at like rainwater harvesting off a roof, you used an approach similar to this. So Q equals CIA. When we multiply these all together, unitless coefficient times inches per hour times acre, we get acre inches per hour. But in fact, the conversion between acre inches per hour and cubic feet per second, the actual unit conversion is just multiplying by 1.008. And since it's so close to 1, we actually just say when you use these units, inches per hour and acres, you get cubic feet per second. And this is going to be the peak runoff. And we'll talk about why in a second. But it's not runoff versus time. It's just what is the peak runoff from that area for that storm. Okay? So I think why it's called the rational method is not because it's such a rational approach to things, but because of the ratio part of it. The C being what ratio of what falls runs off, but I'm not sure. All right, so let's look at the parameters a little bit more in detail. C. So C is this unitless coefficient, table 15.2.3 in your book. That's right there. So we're jumping now from chapter 8 to chapter 15 to do some stuff. This table shows those values of C for different types of areas, similar to the curve number table that we've already looked at, but also has the values of C for different return periods in years. So that return period is saying like a 2-year storm event or a 10-year storm event. Those have different values of C. Again, it's trying to incorporate this infiltration into value of C, and so depending on how intense the storm is, you might have different amounts of infiltration. And anyway, that's what that's all about. If you have more than one type of area contributing to the runoff, you might need to calculate a weighted average C, which is the same approach as calculating a weighted average curve number. So again, forgive the bad mathematical notation here, but like our C average might be equal to like area 1 times C1 plus area 2 times C2 plus etc. However many areas we have that we're contributing, all of that divided by the sum of the areas, right? So A1 plus A2 plus etc. Right? If we do that, we'll get a weighted average curve number for the whole area. I mean, not curve number, C value. Okay, I stands for intensity. We're going to assume that we don't have like a rainfall hiatus graph. We just have a constant intensity for the entire duration of the storm. And this is probably the parameter that needs the most explanation. So if we're looking at where our storm drain is and we're trying to find what the peak flow is at that storm drain, the storm starts over the whole parking lot. Immediately after the storm starts, like within seconds after it starts, the flow rate at the drain is not yet at its peak flow rate for that storm, because the only water that's contributing to the flow rate there is stuff that fell right around the drain. The stuff that fell at the furthest point away has not had time to make its way to the drain yet. Okay? It takes some amount of time for the water at the drain, the water that falls at that farthest point, to get to the drain. That time we're going to call the time of concentration. So we can look down here at time of concentration. It's the time for a drop of water to flow from the remotest point in the watershed to the point of interest. Until that drop gets there to the drain, the whole watershed is not contributing to the flow rate at the drain. So immediately after the storm, the flow rate is very low. As rainfall continues at that constant intensity, the longer the time I give it, the more and more of the watershed that is now contributing to the flow at the drain, until we get to the time of concentration, at which point now every spot in the entire parking lot or watershed or whatever is contributing to the drain. Thus, my peak flow is going to occur once the time of concentration has elapsed from the start of the storm. Okay? So the intensity that I'm going to use is, we'll see in a minute, it's the intensity that's occurring at the time of concentration. So this occurs at the time, right? The peak runoff will occur when the entire watershed is contributing. This occurs at the time of concentration. Okay, so what does that mean practically speaking? I'm going to show you a couple, or just one resource. In your homework, when you're looking at it, it directs you to this. But in Oregon, let's find it a second. Hang on. Okay, so in Oregon, we can look up, this is the ODOT Hydraulics Manual, Chapter 7, Appendix A. If you Google that, ODOT Hydraulics Manual, Chapter 7, Appendix A, you'll find this PDF. And it has these intensity, duration, frequency curves for different spots in Oregon. So if I scroll down, I can find cities in Oregon and what zone they're in. I can look and find Newburgh here is in zone 7. And so I'm going to go down now to these curves, find zone 7. And this is an intensity, duration, frequency curve for zone 7. You can see the intensity on this axis, duration over here, and then these different frequency curves. So what I'm going to do in order to get an intensity to use the rational method is I'm going to calculate my time of concentration, and then I'm going to find that time of concentration on this axis, look up to these curves up here for whatever return period I'm on, and then read off the rainfall intensity over on this axis. That's the intensity that I'm then going to plug in for I in the equation. Okay, so that intensity is saying this is my time of concentration at that rainfall duration. That's the intensity I'm going to use. Okay. All right. So that's I, and then finally A is just the area, watershed area in acres. How do I calculate the time of concentration? Well, there's a lot of different methods. If I look at the next page here, here's a summary of time of concentration formulas. And these are used in, these aren't all for rational method. Some are used for others. So for example, this SCS lag equation right here is the one I presented for time of concentration in the NRCS methods lecture. But the one that's most commonly used with the rational method is the Federal Aviation Administration, FAA formula. It's right here. You can see here's the C, the rational method coefficient. You also need the length of overland flow and the surface slope. So even though this was developed for airfields by the FAA, it's frequently used in urban basins, so for developments or parking lots or something like that. Okay. So yeah, here's a couple. We'll probably also talk about additional, maybe more accurate methods for calculating time of concentration that might be required in a later lecture. Okay, so that is all, and the next video is going to go through an example problem where we're going to apply this.